So if we have something like 3 square roots of 5 over the square root of 2, neither one of those radicals simplify anymore. The square root of 5 is not a perfect square, and it doesn't contain any factors in it that can come out. Same thing with the square root of 2. It's not a perfect square, and it doesn't have any factors that we can take out. So back in the section where we were dividing radicals, if we had a square root on top and bottom, we could reduce them. But once we got to the point of not being able to reduce anymore, most of those problems did not have a square root left on bottom. But what happens if we have a square root left on bottom? Well, there are times where it's not really a big deal. And when I was a student and we were learning about square roots, I don't know that I was ever told why you would want to get rid of a square root on bottom. I even taught square roots for quite a while, and nothing, I haven't looked through this book, I don't know that it ever really tells us why we would want to get rid of a square root on bottom, but let's just quickly mention that. So if I had something like this, no square roots there, what do we have to add or subtract fractions? Common denominator. Well, if I had fractions that had square roots on bottom, it would make it more painful to have to get a common denominator if I had square roots on bottom. So what we're going to look at in this section primarily is what can we do so that we have a fraction that's equivalent to what we start with, but doesn't have a radical on bottom anymore. Fractions are bad enough as it is. If we could do something to make the radical on bottom go away, well, that would be nice. So let's talk about what we can't do. So often on the test, I'll see people do this. They'll say, well, if I've got a square root, to get rid of that square root, I can just square it, and whatever I do to the bottom, I have to do to the top. For some operations, that does work. It is true that when you square a square root, those things do cancel. But if we have a fraction, squaring the top and squaring the bottom almost never keep the fraction equivalent to what it started with. Let's look at an example. If we take this fraction and square the top and square the bottom, we would get 4 on top, 9 on bottom. That's not the same thing as 2/3. 2/3 is actually more than 1/2. 4 over 9 is less than 1/2. Even if we converted those to decimals, those are not the same amount. So when we rewrite a fraction, when we get it at a different denominator or simplify complex fractions, we always want our fraction to be equivalent to what we start with. We just want it to be in a different format. So doing this isn't going to work for us. So what you probably did if you did radicals in high school is, if I have a square root of 2 on bottom, multiply the top and bottom by that same square root. And that will work. On top, we have a 5 under the square root and a 2 under the square root, so we can multiply those together. 5 times 2 is 10. On bottom, if I have a square root of 2 times another square root of 2, 2 times 2 is 4. And what's the square root of 4? 2. So by multiplying by another square root of 2 on bottom, it makes it so that this denominator is a perfect square. So that's the reason we multiplied by a square root of 2 here. So let's look at another one that's similar to that. So following the logic of what we just did, it would seem to reason that we would multiply the top by the square root of 8 and the bottom by the square root of 8. And that will work. I'm going to offer an alternative in just a second to kind of get more to the heart of what it is we're trying to accomplish, but this will work. when we multiply together on top, we have a 3 and an 8 under the radical that we can multiply together. On bottom, we basically have a pair of 8s, don't we? And if we have a pair of 8s under our square root, we can take an 8 out front. Also, you could say, well, 8 times 8 is 64, and what's the square root of 64? 8. Why is the square root of 64 8? Because 64 is 8 times itself. And then we have to reduce this. I say reduce it, simplify. We're not allowed to reduce the 8 with a 24 because the 8 is not under a radical, the 24 is, but that square root of 24 will simplify.
You can pull it too.
Yes. 24 is 4 times 6. The square root of 4 is 2. 6 is not a perfect square, so it stays under the radical.
And if you simplify the 2 8s, considering 2 goes into 8?
Yeah. 2 goes into 2 once. 2 goes into 8 4 times. That leaves the square root of 6 over 4. And that doesn't reduce anymore because 6 is 2 times 3. Neither one of those factors occur twice. So we get the square root of 6 over 4. So what we did there is perfectly fine. But I'm going to offer you an alternative here. And what we did here is perfectly fine, especially when we have just numbers. But the alternative form may be better in some situations, especially when we get into cube roots, fourth roots, fifth roots, or even when we have variables. So let's factor the denominator. 8 is 2 times 4, and that's 2 times 2. So on bottom, we have 1, 2, 3 2's. So 8 obviously is not a perfect square. So what we did on the previous two problems is we multiplied by something that would make the denominator a perfect square. If we multiplied it by itself, that number is a perfect square. Here we multiplied by 2. Something times itself is a perfect square. But we don't have to multiply by 8. We can actually multiply by something smaller. If we're making a square root, we're looking for groups of 2. Well, we have a group of 2's there, and we have one that's not in a group. So how many more 2's would we need on bottom so that everything is in a group? One more 2. If I put another 2 there, notice everything would be in a group. And I can do that. I can multiply the denominator by another 2 under the square root as long as I multiply the top by another 2 under the square root. Because I'm multiplying top and bottom by the same thing, aren't I? And as long as we're multiplying the top and the bottom by the same thing, we're really just multiplying by 1. And when you multiply by 1, it doesn't change how much you have. So let's see what happens. On top, we end up with 6 under the radical. On bottom, we can pull a 2 out for that pair and a 2 out for that pair. 2 times 2 is 4. And isn't that the same thing we got when we did it the other way?
The other way is easier.
So on this one, it probably is perhaps easier. On this one. So I'm not going to specify which way you have to do it, as long as you show your work. But let's suppose we had the cube root of 5 over the cube root of 2. So the whole trick that we did the first 2 times of just multiplying by another cube root of 2 or in our case, we were doing a square root. That doesn't work here. Because if I multiply the bottom by a cube root of 2, that would give me a cube root of 4 on bottom. Is 4 a perfect cube? No. So why does that not work? That doesn't work because when we're looking for a cube root, we're looking for the same factor repeated how many times? 3 times. So if we start out with this 2 under the radical, in order for it to come out, we need 2 more 2's, don't we? Not just 1 2, we need 2 2's so that we have a total of 3. So if I pick up 2 more 2's on bottom, I have to pick up 2 2's on top. Yeah, that's right. I was basically looking for what could I multiply that by to make it a perfect cube. So multiplying it by 4 would make it a perfect cube. So now we have 1, 2, 3 2's on bottom. On top, we don't have any factor 3 times. So nothing is going to come out on top. So we have 5 times 2 is 10, times 2 more is 20. And what can we pull out on bottom?
2.
Yeah. So when we put it on the outside, it'll be a 2. It's the 8 that comes out, but we put a 2. Because when we have 2 cubed underneath, the cube root and the cube cancel, leaving us the 2. So on the top, we're left with a cube root of 20. On bottom, 2. So when we're rationalizing the denominator, we're just trying to make it a perfect root. If it's a square root, we're trying to put enough factors underneath so that the whole bottom is a square root. If it's a cube root, we're trying to put enough factors underneath there so that it's the perfect cube root, so that everybody is in a group. So let's do this. So the cube root of 7 over the cube root of 4x. So 4 is not a perfect cube, and we only have one x factor. So let's see, 4 is 2 times 2. We're taking a cube root, so we need to have the same factor how many times for it to come out? 3.
So you need 1.
So I need one more 2. We have 2 2's here, so we need another 2 so that we have a full group of 2's. Do we need any more x's?
Yes. 2.
2. We have one x here, so we need 2 more to make a full group. And if we multiply the bottom by 2x squared under the radical, we have to multiply the top by 2x squared under the radical. So you don't necessarily have to write the bottom again, but I'm going to. So now we have 3 2's underneath and 3 3's or 3 x's underneath.
You can pull all of it out.
Yeah, we have a group of 2's, so we get a 2 on the outside. We have a group of x's, so we get an x on the outside. And again, remember why. Because if we have the same factor 3 times under a cube root, those cancel. We have an x 3 times under the cube root, so those cancel, leaving us the 2 and the x. On top, no factor occurs 3 times, so it's just all under the radical. 7 times 2, x squared. So our final answer is the cube root of 14x squared, and on bottom we got a 2 and an x.
People that don't understand is try to take the, like, how you're supposed to subtract. Like, I mean, I know you're not supposed to, but like, they'll try to subtract like x squared minus x.
Yeah, that happens. So why can we not reduce the x squared on top with the x on bottom? That's right. The one on top is under the radical. The one on bottom is not under a radical. So right, that's right. So we can't reduce. Same thing with the 14 and the 2. The 14's underneath, the 2's not underneath, so we can't reduce those. Also on the test, make sure to put the 3. If it's a cube root, make sure you put the 3 to indicate that it is a cube root. Yeah, it'll make you not come up with the right number of factors. And also, if you tell me your answer, even if you have the right number of factors,
You don't have the right radical.
you don't have the right radical. So you would still get most credit, but I would count off point, half a point or something like that. Because technically, that's not right. So let's do 5 over the 4th root of 9x y squared. Now we're just getting all kind of crazy.
You would need 3 more x's, 2 more y's, and 3 more 9's? Wait, no.
So that would work. That would work. But 9's not prime, is it? So we could break 9 down and see
3
if
times 3 is 9, so it would be 2 3.
that's exactly right. So that would work to get 3 more 9's. So that would give us a total of 4 9's. But since 9 is made up of 3's, we could just pick up, like you said, there are 2 3's, so 2 more 3's would give us a full group. There's 1x, we need a total of 4 to make a full group, so get 3 of those, and then 2 y's, so that we have a total of 4. Now here's where we have to be careful. Occasionally on these like this, some people will just slide these factors underneath this radical, these factors underneath that radical. That is okay. But in the case we don't have a radical on top,
You would just add it off the radical and keep it in there.
right, that would have to be, if we're putting those factors underneath a 4th root on bottom, we have to put them underneath a 4th root on top. So 2 3's, that's 9, x cubed, y squared. Even though we wrote them differently, that's still the same amount on top and bottom. So the top is 5 times the 4th root of 9x cubed y squared. The bottom, you can rewrite it if you want to, listing all of your factors, but we have 1, 2, 3, 4 3's. So how many groups is that? 1, because we're doing a 4th root. So if we have 4 3's under a 4th root, that's 1 group, so we get 1 3. How many groups of x's? 1, 1, because it's 4. That's right, it's going to be xy, because we have 4 x factors under a 4th root, 4 y factors under a 4th root. So we get a 3, we get an x, and we get a y on bottom. If this would have been 9 here instead of 5, could we have reduced these? Yes. Since that's not under the radical and that's not under the radical, if they would have had something in common, we could have reduced those. We just can't reduce if one's under the radical, one's not. All right, so sometimes they'll be written this way. And they'll want us to rationalize the denominator. You can wait to change it to a single radical, or you can go ahead, you can wait to change it to two different radicals, or you can go ahead and now and change it to two different radicals. Remember, this is the same thing as taking the square root of the top and the bottom separately. So obviously the bottom is not a perfect square. So what additional factors do we need on bottom so that the bottom is a perfect square?
Another y.
We need another 2 and another y. So we could do it either one of these ways. We could leave them all underneath and then break it into 2, or we could go ahead and do this. So either way, we're going to end up with 2 2's, or we could call that 4, 2 y's, or we could call that y squared, and on top we have 1 7 and 1 2, so 14, 1 x and 1 y, and what does the denominator make? 2y. Good. The square root of 4 is 2. The square root of y squared cancels to make y. Notice once we took the square root on bottom, we did not write the square root symbol. That's something occasionally I see. Sometimes after people take the square root, they'll put the answer underneath there, but they still write the square root symbol. Once you take the square root, we don't need the square root symbol anymore. At least for the part that we took the square root. So let me give you a couple. And let you practice these. So let's do that one. And let's do this one. So take a moment and attempt those two. So let's look at the top one. Could we reduce the x's? The x on top or the x on bottom? Is that allowed? It is, because they're both under a fourth root. Do we need to? Well, are we going to need some more x's on bottom to make it a perfect root?
Yes.
We are. We need 3 more. So we could technically cancel the x on bottom with one of the x's on top. But wait a minute, wait. If we do that, no. So I agree with what you said earlier. But if we cancel this x out, with one of those x's, are there any x's on bottom? If there aren't any x's on bottom, there are no x's to need to get rid of. Isn't that true? If we don't have any x's now on bottom, do we need to pick up any x's to complete a group? No, if we don't have even one, we don't have to make a group. So it would be okay to do it either way. We could pick up 3 x's to make the bottom a perfect group of x's. We would just have to reduce at the end. Here we're reducing at the beginning. Now 8 is 2 times 4, which 4 is 2 times 2. So 8 is 2 to the third power. So how many more 2's do we need under our radical? We need 1 more 2, so we need to get another 2 on top. How many more y's do we need? We need 1. We have 3. We need another to make a full group, so we have to do that on top as well. So on bottom, we have 4 2's under a 4th root, so that gives us 2. We also have 4 y factors, 4 factors of y under a 4th root, so that gives us a y. On top, we have a 4th root of, let's see, we have a 1 3 and 1 2, so 3 times 2 is 6. We have 1x and we have 1y. And that's as far as we can go with that. We can't take any 2's, 3's, x's, or y's out of the top because we only have one of each of those.
I think it's just 1. Because I got 3.
On top or bottom? Top. Okay. So if we do it the other way, let's do that.
Oh, wait.
So if we do it the other way, we started out with this on top, this on bottom. So 8 is 3 2's. So if we don't reduce to begin with, then we would need another 2, wouldn't we? And if we don't reduce to begin with, how many more x's do we need? We need 3 and 1 more y. So we need that same thing on top. The 2, 3 x's, and a y. So on bottom, we have a group of 2's, so we pull out a 2. We have a group of x's, so we pull out an x, and we have a group of y's, so we pull out a y. On top, we still have a 3 times 2. How many x's are we going to have? If we do x to the second times x to the third, we have x to the fifth. And then we have a y. That's not the same thing as this, is it? But they should be. That's right. If I have 5 x's, if instead of calling that x to the fifth, if I write 5 x factors, then we have one group of x's, so we can pull an x out front. We have a 6, we have a y, and then we have this other x. And we have this x factor out front, this extra x factor on bottom, and those will cancel. We get to the same place. But if we're able to reduce at the beginning, sometimes that benefits us. So 6. I'm fine with you doing it whichever way. But just if you do it the other way, make sure when you get to here that you do simplify that radical on top. All right, so 49 is 7 times 7. So we need another 7. And whatever we put has to be under a cube root. Yeah, that's x to the second here. So we need another x. How many more y's do we need? We need 2. We have 1 y. We're making groups of 3. So if I have 1, I need 2 more. So on top, we have a 7 out front times the cube root of 7xy squared. On bottom, since we have 1, 2, 3 7s, we can put a 7 out front. Since we have 1, 2, 3 x's, we can put an x out front. And since we have 1, 2, 3 y's, we can put a y out front. And does anything reduce here? That 7 is outside the radical. That 7 is. Those are factors. So that will give us the cube root of 7xy squared over xy. You want to do a couple more like that? Practice. Like this one? Yeah. So let's do 5. Actually, I'm going to change that to 2. Let's do the 4th root of 18, x to the 5th, y to the 2nd. Let's take a look, see. So 18. 18 is 2 times 9. 9 is 3 times 3. So we have a 2 and 2 3's. So that's what's already under the radical. So how many more 2's do we need to put under the radical? 3. And why 3 more? Right. If we're making a 4th root, we need 4. If it's a 4th root, we need something under the radical 4 times to cancel it out. How many 3's do we need? 2. How many x's do we need? Plus an extra one. So that extra one means that if we simplified it right now, if we have 5 x's under the radical, all of those would get to come out as an x, so we would still be left with 1. So how many more do we need so that other x can come out? We need 3 more. If we pick up 3 more, then we have a total of 5, 3 more. Now we have 8, which is how many groups? 2. Yeah, that's right. How many more y's do we need? 2. Good. Sounds like y'all are getting the hang of this. But it's just, we're wanting to build so until we get everything part of a full group. So if we've got 5, we have 1 full group that we can take out, but then we have another one, and we're trying to get everything out from under the radical. So if we got 1, it needs 3 buddies. So that means on top we're picking up 3 2's and 2 3's, so that's 8 times 9, which is 72. Good. X to the third, y to the second. So right now the top is 2 times the fourth root of 72 x cubed y squared. Now on bottom, what do we pull out? We're going to pull out 2. We're going to pull out a 3. We're going to pull out 2 x's, because if we've got 5 and 3 more, that's 8 x's. So we're going to pull out 2 x's, which be careful, because I've seen this. When I say 2 x's, that doesn't mean 2x. That means x squared. That means an x and another x multiplied together, so x squared, and then 1y. Anything reduce? So yeah, 2 times 3 is 6. But if we have a 2 on top and a 2 on bottom that are both factors, we can cancel those. So we're left with a 72 x cubed y squared on top, 3x squared y on bottom. Good. Good.
I feel stupid now.
That's fine. That's fine. If you got to the same location and the steps you show lead us there, that's fine. You could have, did you take the x out first? Got you. Got you.
Yeah.
So we want to do another one of those?
No.
Okay. Okay. Good. Tell us what you really think. No. Okay. So there's one more type of problem in this section, and let's make an observation before we get there. So last week we looked at multiplying radicals and stuff. These two parentheses are called conjugates. They have the same terms. They're not opposites, because the square root of 2's are both positive, but the 3's are opposites. So if we have the same terms, but only the middle sign is opposite, then these are referred to as conjugates. And something special happens when we multiply conjugates together. So let's distribute here. Square root of 2 times the square root of 2. We can write that several ways, but that's all going to simplify the same. So
Is it that the conjugates cancel each other? Because they end up being 3 squared positive, 3 squared minus 3 squared? I worded that horribly. I'm sorry.
So let's see. We'll see. So something is going to cancel. Yeah. When we do root 2 times 3, we would get 3 roots of 2. When we distribute here, we would get minus 3 roots of 2. And times here, minus 3 times positive 3 would be minus 9. Those middle two terms are opposites. The square root of 4 is 2. So if we multiply conjugates together, even if they have radicals in them, we're going to get rid of the radical. So the reason we want to do that is because sometimes instead of having a single term on bottom, we might have 2 terms and one of them is a radical. So if we only had 1 term on bottom, we would just multiply by a square root of 3 to make that go away. But that doesn't work if we have 2 terms. So in this case, to make the denominator not have a square root in it, we're going to multiply top and bottom by its conjugate. So let's do the bottom first. If we distribute on bottom, 1 times 1 is 1. 1 times root 3 is root 3. Negative root 3 times 1, so a negative times positive is negative root 3 times 1. Negative times positive is negative, and root 3 times root 3, we could call that root 9, or you might say, well, if I do root 3 times another root 3, I've got a pair of 3s, so a 3 comes out. Either way, what's the square root of 9?
3.
3.
So it would just be a minus 3.
That's right. So on bottom, square root of 3 minus square root of 3 cancels. You just told me that the square root of 9 is 3, so on bottom we have 1 minus 3. On top, we could distribute that, or we could leave it factored. Either way, we get what on bottom? Negative 2. And our goal was to make the denominator not have a square root in it. I'm not going to emphasize this a lot, but if you have a problem where you have two terms on bottom and either one of them is a square root or both are square roots, then we multiply by the conjugate to make those square roots go away. Let's do one more of those and we'll move on.
So how are the people online gonna, like, they just gotta do the homework or review the homework?
I'm recording right now, so I'm going to save it, and then once the internet comes back, then I'll upload it for them to watch. Yeah. So we have two radicals on bottom. We have things added.
So what do you do minus radicals?
Mm-hmm. That's right. We're going to do that. So on bottom, let's multiply the bottom out first. So root 2 times root 2. That's going to have two 2's under the radical, so we can get a 2. I'm going to write it on the side just in case you didn't see that. If we do root 2 times root 2, that's the square root of 4, which is 2. When we multiply here, we have a positive times a negative. Root 2 times root 7, that's the square root of 14. When we distribute there, a positive times positive is positive. Root 7 times root 2, which is also root 14. And when we multiply here, positive times negative is negative. And when we do root 7 times root 7, we can either call that the square root of 49, or you can say if I've got two 7's, I get a 7 out. So on top, you don't have to multiply that out. If instead of having 5, if we had two terms on top, we probably would distribute that. Yeah. The root 14's cancel. 2 minus 7 is negative 5. And that reduces, doesn't it? That 5 is a factor, that 5 is a factor, that leaves us a negative 1 on bottom, or we could just put a negative out front and call that minus root 2 minus root 7. Remember we said back on the last test, if we have a negative out front, we could either put that negative on bottom, on top, or out front. So we just moved it from bottom to out front.